Welcome to chemisode number, I think it's number 3 actually. It's on the periodic table. So this is the periodic table, and we're going to look through a few different things like how and why the elements are arranged and the trends that can be observed in the periodic table. So let's get stuck straight into this now. As I said, the topics that we're going to cover: the history of the periodic table and the development into what it is today, a bit of a look at today's modern day table and how today's modern day table can be used to find out what the electron structure is for some elements. And then we're going to take a big step sideways and look at the trends that are found in the periodic table, which kind of goes back to how it was developed, but now we know more trends and more things that can be found out from the periodic table. And lastly, a summary of what the periodic table is all about. So now, first of all, let's look at our history. So the history of the periodic table. This man here is called Dimitri Mendeleev. He is a Russian scientist, or he was a Russian scientist back in the 1800s, and he did a lot of work, and basically he developed the first idea of the periodic table. Probably wasn't actually the first one. There was another guy called John Newlands, but Mendeleev extended the idea and kind of published a paper first on the periodic table. So what we're going to look at is his idea and how he came up with his idea for the periodic table. What he did is he's a very clever man, very crazy, but clever. Obviously you can see his appearance there. Looks like a bit of a disheveled old man that might live on the street. But what he looked at is some of the elements behave in the same way, that some elements react in the same way to other ones. And he looked at how, if you arrange these elements in increasing atomic mass, because obviously back in those days they didn't have atomic number, they didn't have number of protons, neutrons, electrons. They had the masses though. So he arranged all the elements in increasing mass, and he saw that some of these behaviors they occurred in a periodic fashion. So every 8 elements had a similar property, and what he did is he kind of arranged them in a certain fashion to show off these properties. The properties were kind of like the formula for the oxides. So when they react with oxygen, when they combine with oxygen, how they group together and bond. So he found out that the first lot of elements that had the same properties, they bonded with 2 metals and 1 oxide. And then the next ones that he found that they bonded 1 to 1, so 1 metal to 1 oxygen atom. And then the next ones, they had 2 metals to 3 oxygens. So he found out that these, the formula oxides, had a ongoing pattern. He saw the reactivity, so he saw that if you looked at the first group that he created, these had a very, very high reactivity, and if you went to the next group, these had a bit of a lower reactivity, but they're still alright. He also saw that some of them have a different metallic color. No, not metallic color, metallic characteristic. So he looked at all these types of different things, and he saw the periodic way that they behaved, basically. He arranged them, as I said, with increasing atomic weights in periods which go across, and he put the similar properties in groups going vertical. And this is the kind of thing that he came up with. This is his periodic table here, you can see. These periods are going across, and the groups going up and down here. Okay, so period 1, period 2, period 3, then group 0, group 1, 2, 3, 4, so on and so forth there. So the things in the group that go up and down, these guys have the same type of property. And as you might see, lithium, sodium, potassium, we might know the alkali metals experiment, or the demonstration, where if you put these guys in water, they kind of have the tendency to explode. So he would have put all these together based around that idea. Moving across, we can see that we have an increase in mass. So helium is quite light, lithium's a little bit heavier, beryllium's a bit heavier, boron's more heavy. carbons, and as we go along they get heavier and heavier. And he saw that this is all increasing and that he can put in these elements as far as we go. Now, you notice here we have a gap. We have a couple of things which have gaps in them. So there's no element in here, there's a little dash here with no element here, there's no element there. Now, this isn't because there is no element that fits in there, but the reason there's gaps there in Mendeleev's periodic table is because these elements were not yet discovered, but all the ones that we had discovered didn't actually fit into his pattern. So obviously as we're going increasing in size, you get to this gap here. Technically, if all the elements had been discovered, it should be this R radon. But because this didn't fit with his theory, his pattern, he decided, nope, there must be an undiscovered element, so I'm going to leave a gap here and put that in there. So these gaps were there because the known elements, they didn't fit his pattern. So what he was able to do was predict where these elements are going to go, where these elements that are yet to be discovered might end up being. So if I move back again, he left gaps due to some elements not fitting in with the patterns that were observed. These elements later on were discovered, and what Mendeleev actually managed to do was predict pretty much exactly what their properties would be. He managed to predict the atomic mass of germanium and a few other things as well. So he was really good at, once he had this pattern he saw, at predicting what the different values would be for the elements to be discovered. So that's a bit of the history. That's Mendeleev. He came up with this idea. This idea, as I said, came up around about in the 1860s. He started getting the ideas, and it wasn't until about 1880 that he actually got this published. And now there's a whole bunch of different monuments around Russia, because he's Russian, of the periodic table. We'll move on, and we'll look at today's periodic table. Today, we have about 118 elements that we know. Not all of them are naturally occurring. Some of them have been forced together, but we got 118 elements. This is a lot more than what Mendeleev had to deal with. He had about 56. Instead of arranging them like Mendeleev did in increasing atomic weight, what we do, because we understand about protons, neutrons, electrons now, we arrange them in increasing atomic number. This makes it a lot easier for us because the increasing atomic number just means it goes from 1, 2, 3, 4, 5, 6, whereas with the increasing atomic weight was going from 1 to 4 to 7. So the increasing atomic number is a lot easier for us. The groups in the blocks, instead of having Mendeleev's groups based around the properties, we group them now based around the electrons in their outer shell and the orbitals that they exist in. With our periodic table, we have trends, and they observed because of these electrons that they have. So even though we don't group them in their due to their properties, they do actually display the same properties because they're grouped upon electrons, and the properties are based around those electrons. So that's a bit of the difference between his periodic table and ours. Moving on, let's have a look at our periodic table. So this is our periodic table. You've seen this before, you've looked at it before, you've probably done your chemical bingo based around this periodic table. Let's have a look at it. Now we have all these elements here. We have two different numbering styles. Groups going down, so our vertical things are groups and our horizontal things are periods. So our groups, we have two ways of numbering things. We have the old style, which is similar to what Mendeleev used, the idea of Roman numerals moving across here. So you've got the Roman numerals, and then you also have this thing called IUPAC, which is basically the international way of numbering things. It's observed internationally. So the IUPAC is numbers for groups, and the old style is Roman numerals for groups. You can use either one pretty much, just as long as you understand that group 7 could be IUPAC in case of the number 7, or it could be VII in case of the Roman numerals. Periods, as I said, they go across: first period, second period, third period, fourth period, fifth period, and the groups go down, and you have obviously 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. What these numbers, the group number and the period number, tell us in terms of the electron structure is the period tells us how many electron shells there actually are, and the group number, it tells us how many electrons are in the last shell. That's the old style. So if you take, for example, silicon, it's in group 4 in the old style, and it's in period 3. So you'd expect it to have 3 shells, and you'd expect it to have 4 electrons in its outside shell. We're going to do a couple of examples on that in a second, but this is the periods and the groups. Next up, we have our blocks. Our blocks, I'll just show you them. This is known as the S block. The blocks tell you about the last subshell that the electrons are going into. Over here we have our P block. In the middle here we have our D block. And last of all we have our F block, where it doesn't really fit in really well. It should technically go in here. So really we should expand this and put the F in here, but it doesn't really fit nicely on A4 paper. But the blocks tell you the last subshell that your electron's going to go into. So here's a couple of examples. What we want to look at is our oxygen. Now oxygen, and we want to try and write down the electron structure based around just looking at where it is in the periodic table. Rather than trying to write out how many electrons it has and write it all down, we want to look at the periodic table and understand a bit more about what oxygen's happening with. Now, the group that oxygen is in, it's in number 6. What that tells me is it has 6 electrons in its outside shell. It's in period number 2, so therefore it has 2 shells. So if I look at what it looks like, I have oxygen looking like this. It has 2 shells. The first one's full with 2 electrons. The second shell is this outer shell, and because it's in group 6, it has 6 electrons in it. Its last subshell has P. Obviously you think about 2s, then 2p. So its last electron will be in the P block. So period 2 means it has 2 shells, and group 16 or group 6 means it has 6 electrons in its outside shell. Another way of representing these guys is called a Lewis dot structure. A Lewis dot structure only shows the outside electrons, and you'll probably draw more of these than this anyway. So your Lewis dot structure just shows the outside shells, and remember the group number tells you how many electrons are in that shell, so therefore the group number is 6, so therefore you have 6 electrons in the outside shell. Now I've got a couple more of these, so I'm going to get you to pause when I come up to the question, and you can write down what you think is going to be, and then I'll show you what the answer is. If you didn't understand this, please go back and replay this little section again, just so you have a better understanding of what's going on. So here's the next one. The next one is chlorine, and there's chlorine there highlighted for you. So I want you to try and write down what the electron structure is going to look like for chlorine. So pause it now, and then we'll go on to it. Okay, you're back, and here is chlorine. It's in group 7, so the last shell should have 7 electrons in it, which it does. It's in period 3, 1, 2, 3. So it's in period 3, so it should have 3 shells in total. So your first shell here has 2, your second shell is full with 8, and your third shell is the last shell, which tells you it has 7 in it there. So group 7 means it has 7 electrons in the outside shell. Our Lewis dot structure, as I said, is the most important structure. Just shows you its last electron shell, which has 7 electrons in it because it's in group 7. Here's your next one. Your next one is magnesium, which is highlighted here. So please try and work out what the electron structure looks like for magnesium. So pause it now and have a go at that. All right, here it is. This is magnesium. It's in group 2, so therefore 2 electrons in the outside shell. Lewis dot structure, as simple as Mg12 here. Our period 3, therefore we have 3 shells, and it's in our S block. Well, just understand that this is the S block because it has 3s1, 3s2 is where these 2 electrons will be at. So there's magnesium. Last one, I think it's the last one anyway, is carbon. I think it's the last one anyway. Have a go at carbon. Pause it now. Have a crack at it. Okay, and now let's look at our answer. Here's our carbon, group 4, 4 electrons, Lewis dot structure, just 4 things around it. And it's in period 2, period 2 is 1, 2, so therefore it has 2 shells. Okay, so that's carbon. And now we're going to look at our trends. So if you want, take a break, pause this, and come back for your trends. Okay, trends in the periodic table. There's a few things, as we said, that obviously the way that the elements behave is based around where they are in the periodic table, and what Mendeleev saw was a pattern appearing with the stuff in the periodic table, and what we're going to look at is some of those patterns in our modern day periodic table and why this all happens. So you have the atomic radius, which is how big an atom is, the electronegativity, which means how good an atom is at taking an electron in, how easily it can attract electrons towards itself. The first ionization energy. The first ionization energy is the how hard it is to remove the first electron, how hard it is to make it an ion. So that's what the first ionization energy is. The ability or the difficulty it has of removing one of the electrons, kind of the opposite to electronegativity, if you will. Then you have metallic character, how metallic an atom acts. Does it behave as a metal? Does it behave as a non-metal? And lastly, we have our reactivity of elements. All these things here, all these trends, can basically be kind of comes down to one thing, really. There's one thing that kind of explains all these trends, and that is this thing called core charge. The core charge of, or the change in core charge across the periodic table is the reason we have periodic variation with these guys here. So let's just have a look at what core charge is first of all. Let's try and define core charge, and then we'll explain this a bit easier. So core charge is basically the pull of the positive charge in the nucleus on the outside shell electrons. So if you imagine we have our nucleus, it's how easy it is to hold in the electrons around it. We've got 2 elements we're going to explain. We've got lithium here and we have oxygen. Both of these guys are in your second period. Lithium is your first element in your second period, so it's in your group 1 of IUPAC and group 1 of your old style. Oxygen is in group 6 of the old style because it has 1, 2, 3, 4, 5, 6 electrons. So this is on your far left and this is on your far right. Looking at lithium here, it has 3 positive charges in the middle. It's got 3 protons. It's got 2 electrons in the middle here, and then it's got 1. See, the core charge is the overall feel that this electron has from this nucleus. Around the nucleus here, we have 2 electrons kind of shielding this electron out here. So what this electron actually feels is positive 1. It feels a charge of positive 1 because it has 3 positives here. 2 of them are being shielded So this feels 1 charge. The oxygen, on the other hand, it's got 8 protons in the middle. It's being shielded by 2, so each one of these electrons here, it feels a core charge, or it has a core charge of positive 6. So can you understand that, where we have the core charge as being the effective pull, the effective amount of, think about gravity, if you will, if you want, a little bit like that anyway. It's how much it's pulling on the outside shell of electrons. You take off what's being shielded, and then you look at how much is being taken in. So if you imagine, this is the way it's going to happen for each period. As you move across a period, you're going to have an increase in core charge because there's more protons in the nucleus, basically. So as you move across, we get more protons, the same number of inside shell electrons. However, you get more and more pull because you have the greater core charge as you go across. So that's what core charge is, and this kind of explains all our different trends. The first trend is atomic radius. So let's have a look at why core charge affects atomic radius, or how it does. This is your atomic radius. Moving from left to right, you have an increase in core charge. So this is our far left one. Think about lithium. And as you move across, you get more and more core charge. So therefore, you have more and more pull on the outside shell of electrons. So therefore, it's pulling those electrons in. So therefore, what's happening is it's decreasing the size of your atom that you have. So moving across the periodic table, moving across a period in the periodic table, the atomic radius decreases due to the increase in core charge and greater pull of the nucleus onto the electrons. So you get more and more electrons being pulled in. As you move down a group, though, it's kind of hard to see here, but as you move down a group, you get an increase in atomic radius. Okay, this is because simply an extra shell of electrons is being added. Okay, so moving down the group, you get an increase in radius, so therefore you have more electrons there to begin with, so therefore you have a larger atom. Moving across, you go smaller. Moving down, you go larger. You can kind of see that there. The next trend we're going to try and explain is, I've forgotten actually, is the first ionization energy. Now the first ionization energy is the amount of energy needed to take out the first electron. Now go back to core charge and let's try and explain this. The first element here, first atom here, it has a small core charge compared with your one over here. So your first element here has a core charge of just 1. Say it has a core charge of positive. This electron is going to be less attracted to here, so therefore less energy is going to be needed to take that electron away. When you go across the period, you get an increase in core charge. What this means is it's holding on to the electron with a lot more strength. So therefore you're going to need a lot more energy to remove this electron. Okay, so as you're moving across a period, your first ionization energy is going to increase because it takes a lot more effort to remove the electrons. So it says here, due to the increase in core charge and greater pull of the nucleus on the electrons, more energy is required to remove them. So moving across, increasing the ionization energy. However, moving down, the opposite kind of happens. Because these electrons are further away from your nucleus, it makes them a bit easier to take away. So therefore, as you move down, you get a decrease in the energy required to take them off. So this, read it here. Due to an extra shell of electrons being added, it is harder for the nucleus to hold onto the electrons. So therefore, not as much energy is required to remove them. So as you're moving across, you have an increase in ionization energy. As you're moving down, you have a decrease in ionization energy because the electrons are further away and therefore easier to take off. All right, so therefore that's what you have. The analogy that another teacher used to use was to think about this core charge as being parents and the electrons as being students. And if you have one teacher or one parent, it's harder for them to, it's easier for the student, the electron, to run away. However, if you have more and more teachers or parents, it's harder for the student to run away. So therefore, you can understand that the first ionization energy is increasing as you're going across. That's one way of looking at it anyway. Moving on, we have electronegativity. Now, electronegativity is the ability for an element to attract an electron. How easy it is to pull electrons into itself. And as you can imagine, due to the increase in core charge as you're moving across from right to left, the electronegativity is going to increase. So the electronegativity is increasing due to the increase in core charge and greater pull of the nucleus on the electrons. It is easier to attract the electrons because you have a greater core charge. Okay, and as you're moving down, the same as the ionization energy, okay, because an extra shell of electrons is being added, it's harder for the nucleus to attract those electrons because they're further away to begin with. So the bigger the atom, the harder it is for an electron to be able to pull it in there. Okay, so therefore you have the electronegativity having that trend in the periodic table. Moving across, it increases. Moving down, it decreases. And again, as I said, all I'm doing is referring straight back to the core charge. So if you remember core charge, you can kind of really think about it and understand how it all works anyway. So once you understand core charge, you're pretty much right for your trends. Next up, we have reactivity, I'm pretty sure. We do. Reactivity. Now, this is it's a bit interesting because metals and non-metals behave a bit differently. And you kind of have to remember or think back to your year 10 and year 9 days of what metals and non-metals do. Actually, just think back to the last lesson because we looked at ions and how they form compounds. But metals, when they want to form a compound, they want to be stable. So what's going to happen is they're going to lose electrons. Okay, so the reactivity of metals is going to be a more reactive metal if it's easier to lose an electron. So as you're moving down a group, what happens is the reactivity of metals increases. This is because it's easier to remove an electron from the element to form an ion. Okay, think about your group 1 alkali metals and the fabulous demonstration that, my class is going to do anyway, in class showing the reactivity of alkali metals. Moving from lithium, where you put it in a bit of water and it just fizzes around. You put a bit of sodium in the water, it fizzes around and catches on fire. Put a bit of potassium in the water, it fizzes around, catches on fire and explodes. And then you watch the video where you got cesium or rubidium. And I'm going to show you the Brainiac video where they actually, they don't do it properly. They put a grenade in a bathtub and show it. But it shows the idea that as you move down for metals, you increase your reactivity because it's easier to lose electrons. Non-metals, however, are the opposite. Non-metals, remember, they have a lot of electrons in the outside shell and they want to gain electrons to become stable. As you move down your periodic table, the reactivity of metals decreases due to it being harder to attract electrons in. Think about your halogens. Halogens are the most reactive nonmetals, okay, because they are furthest to the right of the periodic table, furthest to the right, and they have the greatest ability to attract electrons. But as you move down their group, it becomes harder and harder and harder. So group 7, really reactive, but as you move down, you go from fluorine to chlorine to, what's the next one? Bromine, I think. And then you got iodine. Iodine's, you can see it as a solid. You can see solid iodine, but you really rarely actually get to see the chlorine and fluorine gases in their elemental state because they're so reactive. Same idea with metals, on the other hand. you can see sodium and stuff like that, but they react really quickly. Anyway, that's the reactivity. Metals, they increase as you move down because it's easier to remove electrons, and non-metals decrease as you move down because it's getting harder to attract electrons. Metals always want to lose electrons, non-metals always want to attract electrons. Remember those two things, and remember your core charge and what happens to them. Moving on, our last little thing I think we want to look at is the metallic character, and I don't really need to say a lot on this, but you can imagine as you move across the period, it decreases due to metals wanting to lose electrons, and as you go down a group, it increases because metals want to lose electrons. It's easier to lose electrons as you're going down. If you think about your periodic table, and when you colour it in years 7 and 8, and you colour in where all the non-metals are and where the metals are, the reason you get that step ladder down is because your metallic character increases as you move down and decreases as you move across. So you can imagine that anyway. You can just think about how that works. But your trends mainly are, as I showed you before, where are we? Here's your trends: atomic radius, electronegativity, first ionization energy, reactivity, and to a smaller extent, metallic character. If you understand how those work, you're going to be pretty much right on the ball with how it goes. And you'll always relate all of these things to core charge. Always speak about core charge when you're explaining these trends. Now we're going to move on to our summary. So your summary. This is what you should be able to do at the end of this video. You should be able to A, number the groups, periods, and blocks in the periodic table. Remember I showed you the periods and groups before, all the colours and all that type of stuff. You need to number them. You need to say what they are. You should be able to number the groups both ways, in the old style and the IUPAC way. You should be able to use the group, period, and block of an element to draw Lewis-Dot structures. Remember, the main thing in this is your group number. That tells you how many electrons are in the outside shell, so therefore your Lewis-Dot structure just shows you the outside shell. You need to be able to explain the terms core charge, electronegativity, first ionization energy, and atomic radius. You need to know what those things are. Remember, core charge, explained it before. Electronegativity, ability to attract electrons. First ionization energy, energy needed to remove electrons. Number 4, you need to be able to explain how each of these things, from number 3, change as you move from left to right in a period. Explain means explain using the term core charge, using the term ability to remove, attract electrons, and so on and so forth. You need to be able to explain these things, not just state, explain. You also need to explain how each of the things in number 3 change as you move from the top to the bottom in a group. So remember, don't just state it, you need to be able to explain it. You need to understand why all this happens. So they're the things you should be able to do. Once you have those things done, you should be pretty much right. Okay? If you have any questions or comments, please let me know. My email address is at the end of this video. You also have the Edmodo page, which you've been explained to about before. If you haven't, look at the description of this podcast, of this video, and you'll be able to see the link to Edmodo and the group code. You also have the Facebook page, so like the Facebook page for Chemisode, and you can post questions, queries on that. And shortly you'll actually have the iPhone app to help you with your Unit 1 chemistry, and we'll have a whole bunch of flashcards there. So keep an eye out for that, and I'll let you know when that actually comes out available on the App Store. So there it is, the periodic table, all done.